Okay, so good afternoon, everybody, and I'm glad, actually very glad to introduce my colleague and friend from Manchester University, Professor Michael Anderson. We work with Professor Anderson for the last about 3 years, and the main topic of our common investigations is modeling crystal growth. And Mike is the principal author of the code and the method which models almost every crystalline substance, at least in principle. And our code, Topos Pro, can create the initial data for this program. And this is the background for our collaboration. And we met for the first time 3 years ago in Italy, and since that we made a lot together, and in 2017 we published a common paper in Nature, actually the first Nature paper in Samara region. And after this we understood that the code, the method is really universal, and we can develop it further for other kinds of substances. And the current visit of Professor Anderson here is to develop this code for some other classes of crystalline substances. I already talked to the SCTMS people a bit about this method, about our paper, but of course it's much better to hear from the real author, the main author of this code. So Mike, please tell us about your method.
Right. Okay, well thanks Vlad, thank you for the invitation as well to come to Samara. I'm really enjoying it. I wanted to come in the winter to see what it was really like. I didn't think I'd be giving my talk in a t-shirt though, but it's clearly the temperature difference between inside and out is pretty large. Okay, so what I'm going to talk to you about today is... Yeah?
Please stay near the screen.
Okay, I'll have to go backwards and forwards to change the slide. Okay, so what I'm going to talk to you about is really what's contained within this paper which we published in 2017, which has a slightly complicated title, but the important things really here is that what we're trying to do in essence, we're trying to predict crystal growth. And we have a method now of doing this. But what I really want to do is I'd say I'm a sort of physical chemist, so we do a lot of experiments, and from those experiments we want to understand what we're doing, so we develop models, so we're making simulations, and that's really what's in the second part of the title, is coming up with simulations to describe experimental data. So I think what I'd like to do is describe to you the background behind this paper, and really first of all where the experimental foundations for the paper come, because they're really important, and then I'll go on in the second half to talk about the simulation methods, and that's really what's brought us together with the group here in Samara. Okay, so originally the materials which interested me most were zeolites. These are nanoporous crystals, extremely important industrially. They're used as catalysts, they're used for water softening, they're used for gas separation, amongst other things. And these materials here are, well, the important things are, let's see, that they're porous for a start. They've got these nanopores, about 1 nanometer. The crystal is made up of, I'm not even showing you what the atoms are, but this is a covalently bonded network of atoms. It would be silica, SiO2 would be the sort of archetypal material. But it's a covalently bonded crystal. And I'll just give you an example of a real crystal. So this is a real crystal of a zeolite-like material taken in a transmission electron microscope. So here you can see these white regions here are what we would call large pores. They're still less than 1 nanometer. They're about 0.7 of a nanometer, but these are large pores for this kind of material. And you can see a lovely regular arrangement of the pores, but if you look more carefully, you'll see that there's actually lots of mistakes in the crystal. So down here we have a double pore, and then if you look around the material, you'll see many of these double pores all over the place. So these defects, which are mistakes in the crystal, have been incorporated as the crystal was growing. And if you look even more carefully at the crystal structure, so we start from this pore here, go right, right, left, right, left, right, right, left, right. You have this random stacking of the pores. And this is an intergrowth structure. So these two properties of crystals are, you see in many, many different crystals. It doesn't matter whether it's a zeolite or pretty much anything else. Everything will have defects in it of some kind, and very often you get these intergrowths forming in crystals. And these types of things affect very strongly the properties. These crystals are functional materials. They're used in industry for a specific function, and things such as intergrowths and defects strongly affect the way that they operate. Here's another even more common difference between crystals. So I've got same crystal structure, different synthetic conditions, and yet I've got two very different crystal shapes and very different crystal sizes. So these are quite small crystals, about 5 microns. These are quite large crystals, about 200 microns in length. And again, the shape and the size of crystals is really important for their applications and their functionality. So controlling this in growing crystals is very important. If you look down here, you can actually see, even in an optical microscope, you can see this kind of hourglass shape. This is an optical birefringence. It tells you immediately there's some problems going on in this crystal. There's something wrong with this crystal, but we don't know what. So even in the optical microscope, you can see the problems. So controlling defects, intergrowth, crystal habit, crystal size, very important for controlling the function of materials. So our crystals, the ones we make of zeolites, that's our primary interest, are grown, crystals are grown out of solution. So you've got two phases here. You've got a solution phase and you've got a solid phase from which they're growing. And if you want to think about how you might interrogate what's happening, you can look at the solution phase. We might use mass spectrometry to see what's going on here. We might use NMR spectroscopy. If you want to look at the solid phase, then in particular types of microscopy, I've just shown you some electron microscopy, transmission electron microscopy, but I'll show you actually a lot of atomic force microscopy, which is very useful for understanding how these crystals are growing. But different kinds of microscopy is very useful, and then what I'll talk about at the end is trying to model what's going on, and that's really what has brought these two groups together. So what I'm going to spend almost the entire lecture talking about this part here. I'll spend quite a long time on this and then move on to this. But I'll just quickly mention the first problem as well. Our difficulty, which is really contained in this paper, is that we have very complicated solution chemistry and we also have very complicated structures. So the whole problem, when you step back, looks really difficult, a really difficult problem to solve. So the question is can we simplify this in a way which is intellectually reasonable but without oversimplifying it, that we lose all the details of what is happening. So this is the problem we have. So I'm just going to mention very quickly the solution phase, just to give you an example. So if I took a solution of a zeolite growing, this is a silicon-29 NMR spectrum, and you can see hundreds of different species in solution. Really complicated. In fact, if you look even more carefully, lots of sharp lines, but you can actually see all these kind of broad humps. These are rather important. They don't look important, but these broad humps here tell you lots about the complexity of the solution phase. And if you do lots of some complicated NMR, two-dimensional NMR, you can begin to pick up some of these ring structures which are forming in solution. These are silicate ring structures, of which there are many. So it's complicated stuff. That's all I want to say about the solution phase. So I'm just going to move now to the solid phase. I'll mention it later on, later in the lecture, the solution phase, what we do with it. Okay, so let's start. We're going to start with a zeolite, which was our starting point, and eventually we'll move on to lots of other different kinds of crystals. So here is a very important zeolite. It's called zeolite A. It's one of the primary components of washing powder. So if you go and buy some washing powder, look at the ingredients, you'll probably find up to 30% of it is this material, and it doesn't even wash your clothes. It doesn't wash it. All it does is it softens the water, so it extracts calcium and magnesium from the water when you're washing your clothes. So if you use washing powder, right now you are covered in this zeolite. Okay, on your shirts. This is one of the biggest components of house dust today. And these are little crystals. They're white crystals. So everybody's wearing a black shirt. You can't see them. Why can't you see them? Because they grow the crystals smaller than the wavelength of light, so they don't scatter the light. Okay? So there's one example straight away where you have to control the crystal size, otherwise you have a problem. You look like you have hair. if you have hair. Okay. So here's the structure of zeolite A, important crystal. It's made up of these cages. So there's this medium-sized cage, a small cage, and then internally there's this much larger cage inside. If we think about the extended structure of the crystal, then what would be important when the crystal is growing is what is happening at the surface of the crystal. And at the surface of the crystal there will be structures at the surface of the crystal. I've shown you the example of a step on the surface of the crystal, and that step here on the surface of the crystal will have some shape to it as well, and the shapes of these terraces, called terraces, contain a lot of information about the thermodynamics of how the crystal is growing. That's what I'll come on to show you. Okay, so crystal growth. Go and get a textbook on crystal growth. This is what you'll find on page 1 of a textbook on crystal growth. So two fundamental mechanisms for how crystals grow, either layer by layer. So we've got a terrace here growing on the surface, nutrient coming from solution, attaching to the surface, migrating to the step edge and joining the step edge. So that's layer by layer growth. Or if you have a screw dislocation in the crystal, so this is a line defect which starts here and runs through the crystal and will come right out at the bottom of the crystal. So it's a line defect. So if you have a screw dislocation, you can form this growth front, this step edge, just like you have a step edge up here. You've got another step edge down here. And as this progresses, you end up with this spiral growth front. Now, the good thing about this is that you never have to nucleate another layer. So here, when this grows across, you have to nucleate a fresh layer, and that's a high energy process. Down here, you've always got this growth front, and you can add to that growth front, and this is a low energy process. Okay? I'll talk about what I mean by high energy and low energy in a bit. Okay, so let's just look at a little bit of data here. So here's a zeolite called zeolite beta, it doesn't really matter. Here's a transmission electron micrograph of it, and here's the surface of the crystal. And if you look very carefully at the surface and you simulate it, you can actually work out the structures which are present at the surface of the crystal. So we find, in this particular case, you've got 3 different structures present at the surface of the crystal. This is quite important information because if the crystal is growing, you want to understand how it's growing. It's good to know how the crystal is terminating as well. But this is very difficult to do. Really difficult work. And you have to remember also in an electron microscope, you're looking in transmission all the way across the surface of the crystal. So it's quite difficult to interpret exactly what the images mean. A better way to study the problem is to use atomic force microscopy. So here is a crystal of zeolite A, remember the one that's on your shirts. It's about 5 microns in an optical micrograph, and superimposed on top is the atomic force micrograph, and you can see very clearly the terraces growing on the surface of the crystal. And the nice thing about the atomic force microscope is the resolution in vertically is about 1 angstrom, so you can very easily look at these terraces, which may be typically 10, 11, 12 angstroms. You can see them very clearly, and the lateral resolution is ideal for looking at the separation between the terraces, so you can very easily pick up all the terrace information with the AFM. So we do a lot of experiments with this atomic force microscope. Here, the atomic force microscope is just this blue thing in the middle, and the rest of this is just an optical microscope. This is an inverted optical microscope. So this allows you to look, it's actually designed for looking at cells, but we put crystals in there. So you can find the crystals with the optical microscope, you can find the facet of the crystal you want to look at, and then you can position your AFM onto the facet of interest. And the big advantage here over electron microscopy is you can do your experiment in solution. So this would be your crystal specimen. Here is the tip from the AFM, atomic force microscope, which is going to come down onto the crystal surface and scan across the crystal surface. And you can put this in air, you can put this in solution, you can heat and cool the solution. The only proviso is because you need a laser light to detect the back of the cantilever, the solution must not be opaque. So it can be coloured, it can be clear, but it cannot be opaque. So if you have particles in there, you have a problem. So you can grow your crystals while you are recording the atomic force micrograph. Okay, and I'll just give you one other technique which is quite important for us, and that is a scanning electron microscopy. So this crystal here, this half of the crystal was done with SEM, and this is the AFM here. So this is electron microscopy, atomic force microscopy, and you can actually see all the terraces quite well even in the scanning electron micrograph. This is done in high vacuum. This can, if you want, be done in liquid under solution as well. But this is quite a good technique because you can quickly look around lots of crystals whereas this is quite a laborious technique. It's quite slow to collect the information. Okay, but the other thing you should notice is that from the AFM you can measure the heights. You take a line across here, you can measure the heights of these terraces very accurately. So here, I'll give you an example of an AFM. So here's the crystal of interest. We're using the inverted optical microscope to find it. Here's the tip of the AFM. We're going to bring the tip onto this 110 facet of the crystal. And if we do that, in solution, we can see the crystal growing. So you can see screw dislocations here, one there, another one here. You can see layer by layer growth going on over here. In a bit you'll see a nucleation, there's a nucleation, surface nucleation. High energy process, another high energy process. And then the terrace is growing. Another one came up here. Okay, eventually we stopped. I'll just play it once again. Just look in this region here at the beginning of the. So just look in this region here. At the moment, you can see lots of nucleation everywhere. You see lots and lots of nucleation. But as the crystal grows, you'll start to see that the amount of nucleation is dropping quite quickly now. And the reason it's dropping is because the supersaturation of the solution is dropping. So as it's growing, we're using up the nutrient from the solution. The supersaturation is dropping. The supersaturation is the driving force for the crystallization. And we have a process called Oswald ripening. Maybe you've heard of Oswald ripening as the process goes on. So it's quite a nice image because you see the two classic mechanisms of growth in the same image. And I should probably just, I wanted to stop it at the end, it's gone, let's get it, I'll get this too. Yeah, you can see that if you look at the terraces, they have very, very specific shapes. So in this case you've got a point at the top and a point at the bottom, and then these kind of rounded features. This is a specific crystallographic direction on the surface of the crystal. And again, as I said, these shapes contain a lot of information about the thermodynamics of what is happening in the crystal. If we look in another part of the crystal, we see quite a nice feature here. So you've got these what looks like layer by layer growth, but in the middle you've got this heart-shaped feature here. And if I just let that crystal grow, the heart is now beating and it's pumping out new terraces. Another terrace is going to come out here. And what's happening here is something which was conjectured back in 1950, something called a Frank-Reed dislocation loop. You have a screw dislocation here and a screw dislocation here, spiral growth, so this will be left-handed and right-handed spiral, and as the spiral grows it gets larger into this heart shape, and then eventually this will connect here and then give you a new terrace here. So this is not layer by layer growth, this is actually they're probably connected actually, so because you see a lot of these. So this left and right hand will go down into the crystal, remember they're line defects, and they'll be connected to one another inside the crystal, going down and back out like that. If we go and look at lots of different crystal systems now, this is a silico-aluminophosphate, metal organic framework, zinc phosphate, lots of different crystal systems, and these are just a collection of screw dislocations in all these different kinds of crystals. And the first thing you can notice is that the shapes of all those screw dislocations in all the different systems is completely different to each other. And this is reflective of the underlying crystal, and it's reflective of the thermodynamics of how each of these crystals is growing. Okay, so just give you another example, just so we can begin to think how we're going to tie this together with the theory. I'm going to give you a screw dislocation, a rather nice screw dislocation on this zinc phosphate, which gives you this nice interleaved, quite complicated pattern on the surface. And you can actually see that growing. This rather complicated screw dislocation now, generating this interleaved pattern on the surface. Very beautiful. All these things that you look at are really quite beautiful to look at. We can see what's happening quite easily. We go look somewhere else on the crystal where it's growing by layer growth. You can find these layers are growing very rapidly in this direction and slowly in this direction. But if we go down half a unit cell, you find they're growing very rapidly in this direction and very slowly in this direction. So every time you go down half a unit cell, the fast and the slow directions switch. If you superimpose a screw dislocation on that, you get this interleaved pattern, this complicated pattern. And the reason you have this fast and slow growth rate is because this is a zinc phosphate, and in the structure the zinc and the phosphate are alternating, zinc, phosphorus. And when you go down half a unit cell, you find the ordering switches by 90 degrees. So it's due to the zinc phosphorus ordering which is causing this pattern. And you can then find strange things going on. So here is an example where you've got fast growth here, slow growth here, but in the same level, without going down half a unit cell, fast growth here and slow growth here. And along this line here, you've got a defect running in the crystal. So probably here, you've got a problem with the zinc phosphorus ordering has suddenly switched, and there's a defect running in the crystal. These are things you'll only pick up with AFM. There's no other technique which you'll see these strange kinds of defects. And if I go to another facet of the same crystal, I'm now on the 111 facet, there's a rather beautiful screw dislocation here. If I just let that run for a bit. Okay. So apart from being again rather beautiful, you can see a few things happening here. So we've obviously got a screw dislocation. The shape of the spiral is more or less triangular. It has some threefold symmetry, I think you'd agree. It's not a perfect triangle, but it's got threefold symmetry. That's the 111 axis, and you have threefold symmetry. This is a cubic system. So not unexpected. However, you can also see layer by layer growth going on over here, and this is not triangular. This is isotropic. It's growing the same in all directions. And then if we measure the height of this, we find that this is exactly twice the height of this here. So what's happening? You can just look at the structure and you can see what's happening. So here's the 111 facet. We've got one step which is half the height of the other step. This one is isotropic, this one is triangular. If you look at the covalently bonded units, they're not connected to each other here. The only thing which is keeping this terrace together is water, hydrogen bonding, cations sitting in between, but there's no covalent bonding in the terrace. So remember, this was kind of isotropic. Here you have complete covalent connectivity. So the message is, you have strong bonding in the layer, you pick up the underlying symmetry of the terrace. You have weak bonding in the layer, it can't really see the underlying symmetry of the structure. So there's a relationship here between the structure you can see in the shapes of what you generate on the surface of the crystal. Okay, so that's kind of going to move on from those AFM images to start thinking about how are we going to extract information. We want to extract thermodynamic information from what's happening, and we're going to try to do that by simulating what we are seeing in these images. And our work starts from, our starting point is this paper by Hugo Meeks, which was published back in 2004. He had a Monte Carlo program which he developed for looking at crystal growth, and I'll try to explain it to you briefly. It's a very thermodynamic paper. I'm just going to put everything into a graphical manner, but what he was saying in this paper was, let's suppose I've got some growth unit looking like that, which is going to grow finally into the crystal. So there's the growth unit inside the crystal. It's going to be in some solvent, so in solution there will be some solvation. And for this to get from here to here, it's got to go via the surface of the crystal. So we're going to start here, we're going to desolvate, and then we're going to attach to the crystal. Or we're going to desolvate more, attach to more crystal, and so on. So there are going to be many sites on the surface of the crystal with different levels of desolvation. And then eventually it will become bulk crystal. And from an energy profile, the highest energy is the growth unit in a vacuum. Here's the growth unit in solution. Here's the growth unit in the crystal, lowest energy. So if we want to grow via this surface site, we've got to desolvate and then grow here. Or desolvate more and grow here. And let's suppose we're going to grow on that site, what's argued in this paper, that the crucial thermodynamic energy is the difference between the energy of this site and the energy of this bulk site. So this energy here is your crucial energy here. If you want to grow on the next site down, this becomes the crucial energy. On the next site, this is the crucial energy. So there are many of these energies for each site on the crystal surface. And if you do that, you can then get the probability that you will grow at that site and the probability you will dissolve from that site depends upon all these delta U's, of which there are many of them. So these are all the delta U's for the solid. The only other thing it depends upon is the driving force. So the supersaturation of the solution. If this is high, you get lots of growth. If this is low, you get lots of dissolution. And somewhere in between, when you get to saturation, the rate of growth and the rate of dissolution becomes equal, and everything is at equilibrium. So the trick then becomes to work out all these energies here for these different surface structures. Okay, so I'm going to give you one more crucial experiment which then ties in with what you're doing here in Samara. Okay, so it's a final experiment. So this is something we published back in 2010. We were working on a crystal system called Zeolite L, which makes these hexagonal prisms. So you've got these side faces and the end face. And the structure of the crystal is one-dimensional channels with these 6 columns, these canker-like columns, which are stacked around the central cage. And the height of these structural units, of one structural unit, is 1.6 nanometers. So if we look at the side surface of the crystal, there's an AFM of the side wall. Here's the C-axis, that's the long axis of the crystal. And you can see these very long terraces growing along the C-axis, very rapidly along the C-axis, very slowly in the AB direction. Okay? The height of the terraces, 1.6 nanometers, as we expect. So each one of those is 1.6 nanometers high. We're not going to grow the crystal here, we're going to dissolve it. We're going to try to dissolve it in a sodium hydroxide solution. So, just watch one of these terraces, say that one there. Watch it dissolving, very rapidly dissolving in the C direction. Whoop, and whoop, it's gone. So it's dissolved really fast in the C direction, it's not dissolved in the AB direction at all. Now we do another experiment, slightly different experiment. We dissolve it, but this time, while we're dissolving it, we actually scan the AFM tip backwards and forwards across the surface of the crystal. And we reduce the concentration of sodium hydroxide, so even the growth in the C direction is now very, very slow. But we're going to help the dissolution with the AFM tip. So we're going to it's almost like scratching the surface, if you like, backwards and forwards. And eventually you can see you cut through the terrace, so it's been cut through here, dissolved away. But if we look at what's happening, it's quite interesting. So, here, as a function of time that we've been scanning backwards and forwards, we measure the height of the terrace. So it starts at 1.6 nanometers high. And it's stable for 2,000 seconds. So it's quite stable. But then it starts to dissolve. And it goes down to 1.4 nanometers. Remains stable for a few hundred seconds, down to 1.2, a few tens of seconds. And it goes in 7 stages until it's actually fully dissolved. And these have differing stabilities as you go through. And if you look at the structures of each of those stages, they all have one thing in common. They're what we would call closed cage structures. A bit difficult to see here, but if we just go back to the zeolite A example, so for us this would be a closed cage, and immediately you can start to see topos comes in. So these closed cages, where this would be, say, a silicon here connected to 3 other silicons through oxygen, what we would call a Q3 site. These are the metastable surfaces. If I remove one of those silicons there, open up the cage, it becomes much less stable. But these closed cages are metastable steps in the growth. Internally, once they're fully condensed, they're all Q4. So these cages, as they are metastable, they become rate determining in the growth. They're not the growth units. It's not what's in solution. We know in solution it's a mess. Things grow, dissolve, attach, detach. But if you form a closed cage, it becomes persistent and therefore becomes rate determinant. So in any kinetic Monte Carlo algorithm, what you need are the rate determining steps in order to speed up the calculation. And these closed cages fulfill that criterion. Okay, so for example, here's a closed cage on the surface of a crystal. We know that in solution that will be at a high energy, and in the bulk crystal, that will be at a low energy. So we've got three structures of the white cage in 3 different environments, and we can put those onto an energy scale now. So we put this at the highest energy, this at some intermediate energy, and this at the lowest energy. And the reason we have 49 rungs on this ladder is because there are 48 sites on this cage, and each one can either be Q3 or Q4. So that's 48 Q3, that's 48 Q4, and that's somewhere in between. That's a mixture of Q3 and Q4. And you can have all the structures, you know, are technically possible in between the top to the bottom. Then remember, this is Zeolite A. There are 3 cages. That's the largest cage. There's a medium-sized cage with 24 sites, so 25 rungs on the ladder. That would be, for example, one of the surface sites. And then there's a small cage with 8 vertices, so 9 rungs on the ladder, and that would be the highest energy. So these will be all your delta U's for the calculation. Then you just need to add in the delta mu for the solution. So if this is high, then the crystal will be dissolving. If this is low, if this is high, the crystal will be growing. If this is low, the crystal will be dissolving. And somewhere in the middle, the growth rates will be equal. So you can see, let's suppose we have it at this level here. Any sites above this will be in dissolution. Any sites below this will be in growth. So here we've got all these are in growth. These ones are in dissolutions. The ones just about the same level, that site will be equally growing and dissolving. So what you can see is we've taken our complicated solution phase, and it's just contained all within the driving force here. We don't have to worry about it because what's controlling the process are these metastable structures on the surface of the crystal. And that's really the point at which I met David in Vietnam. Probably gave the same talk, I imagine something similar. And he was obviously looking at these structures. This looks just like what we've got with Topos. And of course, these tilings, these 3-dimensional tilings, are a lot of them have these closed cages, which is the first thing which interested me. So I was interested in the fact that these were indeed all fully Q3 closed cages. That's a particular structure, and that's the CHA structure. Here's the AEI structure, different tiling, but all closed Q3 cages. And so I was like, okay, immediately we've got our rate determining steps, which was the problem I was wrestling with, that we can feed into a Monte Carlo calculation. Of course, it's not that simple, because if you look at the 3-dimensional tiling for other systems, like Zeolite L here, you find that some of these tiles are not all Q3, but they've actually got Q2 in them as well. So then the question was, well, are those also legitimate to be using? And I think we convinced ourselves eventually that it actually was still the lowest energy way to partition the space, and therefore these will still be potential metastable steps in the growth. And that's a very important Zeolite MFI. Can get very complicated, but now immediately there's this way to uniquely partition it into the what will be the metastable steps for a Monte Carlo code. So what we did for the Nature paper, what we set about doing in this work, was to get a new Monte Carlo code that could determine the growth energetics for any crystal structure, not just a zeolite, but for any crystal structure. Could we do that? So what do we want to do? We want to determine the habit, that's the shape of the crystal, and we need to determine the surface topography from the AFM, all within one simulation. the experimental data we have is crystal shape and surface topography. Those are our experimental parameters. We need to be able to immediately determine all the growth sites, so many sites on the surface, each with a different delta U. We need to be able to compute those immediately. Then if we grow, we need to determine the consequence on all the neighbours. As you grow into a site, what happens to all the neighbours around? We want to do this efficiently, because we would like eventually to grow reasonable sized crystals. Some properties you can see in small crystals, but some properties you need to get micron sized crystals to see the properties. And ultimately, but we haven't really done this yet, we would like to be able to include defects, additives, intergrowths. So we mentioned defects and intergrowths. Additives, people in industry or anybody growing crystals very often will add extra molecules into the synthesis which will stick to or bind to certain surfaces and poison the growth on certain surfaces, and this will change the morphology. So can we, we've managed to do that, this one here. These two are still a work in progress. This is the hardest thing to do, really. So, give you an example. So go back to zeolite A. Three cages, 3 tiles, so not cage now, 3 tiles now. Experimental data, crystal habit, surface topography on three facets. And then you can, using the methodology, putting topos together as an input, and that those ladders of energy levels, you can grow the crystal in silico. You get the crystal habit. You can now see some Oswald ripening going on. So we started with high supersaturation, and now we're dropping down towards equilibrium. So this has come towards the equilibrium structure now of what you would expect for a certain set of energy levels. So you can do this very quickly in the computer. So here we've taken the 3 cages, the large cage, the medium-sized cage, the small cage. We've changed the energy spacing in the ladders, and each one of these is a calculation. And so I'll just take one calculation. There's one of them. This is wrong. Another one, this is wrong. Another one, this is getting closer. And you can do, if you want thousands of calculations, and eventually find where the match with the experiment is. So this is one way to use the code in order to refine the energies, the thermodynamic energies for the particular crystal structure. The key, as with everything, is you must have more experimental observables than parameters that you are fitting in the simulation. So you want an overdetermined problem, and that's what we've succeeded. So remember right back at the beginning, complex solution, complex crystal structure. But we've actually reduced it down so we've got more observables than parameters that we are fitting. So we've really simplified the problem a lot. And a benefit of this is you can also get the structure of the surface of the crystal comes out of the calculation. This is very, very difficult to determine experimentally from electron microscopy. So that's quite nice. You can see, this is Zeolite A. You can add screw dislocations. So here is a screw dislocation running from the top, coming out at the bottom. So there's the bottom of the screw dislocation running through and out the top. And you can see the effect of adding the screw dislocation is, this was cubic, but you now elongated the crystal along the screw axis because it's easier to grow on a screw axis, on a screw dislocation, than it is layer by layer growth. So you immediately lengthen the crystal. Let's go. flip through some of these. It's an equilibrium structure, again for zeolite A, with a screw dislocation. What else we got? Oh, that's the one from the Nature paper. This is it growing in silica via the screw dislocation. So that's sort of high supersaturation now, and coming down towards equilibrium. Okay, so we can now easily go to a different structure. We can just flip to, this case, this is Falgesite. Crystals are octahedral crystals, 1-on-1 facets, triangular topology on the surface. The orientation of these triangles has the point going towards the long edge of the side of the crystal. Three tiles, different tiles, immediately computed. So the problem has been set up really within minutes to set up a new system. And so you can grow the crystal in silico according to a set of energy levels, and you can simulate both the crystal habit and the surface topology. I'll just let's do the rest of it. So you can see what we're actually simulating are these, we are literally growing these cages on the surface. So I can stop this at a crucial point. Okay, so this is visualization software which Adam at the back there has written for the program. So this is actually this is the result of the computation, and you can see that very nicely the terraces growing on the surface of the crystal, as you expect. But if you cast your eye around, you can actually look over here. You can see missing units here. There's a missing unit there. So these are essentially defects, because this has a probability to dissolve back off into solution. Okay, so it's growing and dissolving all the time. It's got a possibility to do them both. So you can begin to look at density of point defects in crystals as well, which I'll come back to in a moment. I'm just going to skip over that. So you then got this problem, as I said, of going from structures which are all Q3, such as Camazite here, to more complicated structures which contain Q3s and Q2s in the tiles. And if we take, this is I think the most complicated zeolite currently known in terms of tiling. So 16 tiles in this particular zeolite. These are the 16 tiles. Here's the experimental data. So we've got these kind of intergrown crystals, but you can sort of see the shape of the individual crystallites. And we've got the surface topography. And okay, so this is now using Topos to input the tilings to the Monte Carlo program. And in fact, we've only got one parameter which we're refining in this particular case. And for such a complex system, we can get the correct habit and get all the correct surface topography that we're seeing on the crystal as it's growing, correct terrace heights, etc. for a really complicated system. And remember back to this thing here, so I showed you back at the beginning, I showed you these crystals here with this strange optical effect of this hourglass shape inside this birefringence. Well, we weren't expecting this to come out of the program, but we can grow these crystals in the program. But actually, if we look internally in the crystals as they grow, we see that the density of point defects which we get exactly mimics the optical birefringence that we're seeing. And the reason is that the defects which are being incorporated because of growth off this facet are different to the defects being incorporated on growth on that facet, because the mechanisms of different facets is actually slightly different. So the defect density and type of defect incorporated is different. And so probably what you're seeing here in this optical birefringence is just different densities of point defects in the crystal as a result of the growth mechanisms being different in different directions. We had no idea that that was going to come out of the calculation. I'll skip over this, I don't have time for that. It's the same thing for this structure, again, point defects. You can use it for metal organic frameworks. Some of you are interested in those here. So it works quite well for metal organic frameworks. So this is something called HCUST1. So again, quite a complicated structure, but we can incorporate screw dislocations as we see in reality into the structure. MOF5, we can see switching between different habits that we see in reality by changing the conditions in the synthesis. So we've gone from zeolites to metal organic frameworks using exactly the same methodology, just one program, one Monte Carlo program, where we can switch in between any of these structures. And then kind of what we're dealing with here today, actually is why we've come this week, is to look at molecular crystals. These are very important in particular the pharmaceutical industry, whereby now the molecule is at the centre of some voronoi polyhedra, and the facets of the polyhedra now represent the interactions between molecules, whether those are van der Waals interactions or hydrogen bonding or whatever. But again, we can essentially put it in exactly the same way into the Monte Carlo program and immediately simulate what we're seeing for the habit of the crystal and also the surface topography of the crystal. Calcites, so this is now moving to ionic crystals. So you've got Ca2+, CO3 2-, and again just you put in the calcium and the carbonate ions, just like with the urea at the centre of voronoi polyhedra. You can put additives in, so these purple dots represent specific sites which have been poisoned. So you can look at the effect of poisoning specific sites on the surface and see how that changes the habit of the crystal. And this is, we can be thankful to the referee for the Nature paper for this one, because this was originally not in the Nature paper, but they asked us, hey, try looking at something like it. They actually gave us a list of things. One of them was L-cysteine. So we had a crack at L-cysteine just to get it past the referee. It turned out to be quite interesting. So L-cysteine, quite an important molecule in various illnesses in the body. The crystals of L-cysteine grow. This is not our work, but this is a very nice AFM work on L-cysteine growth, and you get these typical screw dislocations with these pinwheels. So you get large steps and then sub-steps going around in a pinwheel structure. And we pretty much set this up within maybe a couple of hours of not knowing anything about L-cysteine into the software. And you could indeed simulate pretty much everything that you're seeing and get out the energies, the relative free energies of crystallization for the individual processes for really quite a complex growth structure in quite a reasonably easy manner using this approach. I mean, to the point where even if you look at features on the surface, so what we notice in a lot of the AFM images is you've got to have these sort of what I call a growth overhang. Now this step edge is trying to grow out this way, but it can't. There's this growth overhang preceding the growth, and we can simulate these quite well. And what's happening here is that this step edge doesn't want to really grow. It's got a very slow growth. That's why it's straight. So it doesn't really want to grow that way to the left. And the way it grows to the left is actually by molecules attaching to the side of this big step edge. So the big step edge there, molecules coming in from the side, growing up to the edge here, and then dripping around the edge here and adding on this way. So actually, growth on the C face here is being controlled by growth on the A face. Completely counterintuitive. So and people want to change the morphology of L-cysteine, they're keen to do that. So if you want to poison certain sites to control growth on the C face, you actually need to be attaching molecules to the A face, which is, as I said, very counterintuitive. Let's pass over that. And this was quite interesting. What Rimmer had noticed in his AFMs, when he looked at the screw dislocations, he found they were all right-handed, which is odd. Why are they all the same handedness? And because if you've got screw dislocations, half of them should be left-handed, half of them should be right-handed. No reason why they shouldn't be. But they were all spiralling the same way, so the spirals were going around the same way. And what we found is when we put in left-handed or right-handed screw dislocations, yep, the spirals go around exactly the same way. They just go around the same way. And the reason they go around the same way, even when we change the handedness of the screw, is because the handedness is not controlled. The spiral growth is not controlled by the handedness of the screw. It's controlled by the underlying symmetry in the unit cell. And there's a 6-1 screw axis in L-cysteine which is spiraling a certain way, and all the growth rates go in that order. So it doesn't matter, they're always going the same way. And you can actually see, if you look towards the middle of the screw, you can see one of these is kind of fighting against the handedness of the screw. So the symmetry here, the symmetry of the unit cell is the same as the handedness of the screw. Here the symmetry is opposite to the handedness of the screw, so it's kind of fighting against it. And the only way to reverse the screw is to go to D-cysteine. Okay, so you go from L-cysteine to D-cysteine, you change the underlying symmetry, and then it will spiral the opposite way. So there's actually nothing unusual about the fact that they all look like they're spiraling the same way, but they hadn't figured it out, and I wouldn't have worked it out without actually doing this modelling. So that's quite nice extra information coming out. Okay, so obviously this has been done with the help of lots of people over many years. I've just shown you a little bit of the experimental data that we have. We've had funding. Our main funding, believe it or not, has come from industry, which is odd because it's very, very academic work here. We've had some funding from government, but we have more funding from industry. And in particular, ExxonMobil was very, very helpful in funding us at the beginning, getting things going, but other funding societies. I have to thank the people, David and Vlad in particular, for helping us recently to get this over the line with the Nature publication. And